Hey everyone, and welcome to today's Explainer. Okay, so let's just dive right into this. For decades now, our digital lives have been entirely trapped on flat screens. But right at this very moment, we're undergoing a massive technological shift. It's a dimension leap, really, going from the strict limitations of simple 2D images straight into the absolute magic of AI-generated, fully realized 3D realities. Today, we're going to explore exactly how computers are finally learning to see the world the exact same way we do, with true depth. To really get why this is such a huge deal, we kind of have to start by asking a pretty fundamental question. What actually happens when the world loses its depth? Think about it for a second. Our universe is inherently volumetric. We live in 3D. But a standard camera takes that rich, deep space and brutally flattens it out onto a 2D plane. It's a trap, honestly, what experts call the flatland trap. And when a computer tries to navigate the real physical world using only that flatland data, well, things can get pretty dangerous. Look at this stark contrast here between what a simple photograph loses and the insane capabilities that true 3D vision unlocks. When you're just relying on 2D, you lose so much. You lose accurate scale, you lose absolute distance, spatial relationships just vanish, and objects block or occlude one another. You literally can't tell what's going on behind the stuff in the foreground. But the moment we give AI the power of 3D, we immediately enable life-saving technologies. We're talking autonomous driving, precise robotic grasping of physical objects, and completely seamless augmented reality. We move from just looking at a picture to actually interacting with a physical space. So here's our roadmap for today. We'll start with the flaw of 2D vision, move into the building blocks of 3D, how we make sense of point clouds, fusing sensors together, rendering new realities, and finally the AI generation leap. Let's get into it. All right, Section 1, the flaw of 2D vision, escaping flatland. This right here brilliantly illustrates the core issue we're dealing with, perspective ambiguity. Just imagine a tiny, small sphere sitting right in front of a camera lens, and then a massive sphere sitting a whole mile away. Because the z-axis, the actual depth, is completely collapsed when you make a 2D projection, those two vastly different objects can look entirely identical in a photograph. This scale ambiguity is exactly why 2D is inherently unreliable for spatial reasoning. I mean, if a self-driving car can't tell the difference between an actual pedestrian and a life-sized poster of a pedestrian, you have a major problem on your hands. So how do we fix it? That brings us to Section 2, building blocks of 3D, the language of depth. There are really four primary ways we can encode the 3D world into a computer. First up, we've got point clouds, which are basically just sparse, raw coordinate data straight from a sensor. Next are voxel grids. You can kind of think of these as 3D pixels stacked up together. Honestly, a lot like Minecraft blocks. Third, we have polygon meshes. Those are your standard vertices and faces that you'd see in video game graphics. And finally, the absolute leading edge, implicit or neural representations, which actually use continuous mathematical functions to define a surface. Now, the crucial thing here is understanding the trade-offs of these different encodings. Let's look at voxel grids for a second. They're great because they let us use standard 3D neural networks, but there's a catch, and it is massive. 16 million. That is the number of individual voxels required to map out just a modest 256 cubed grid. The memory cost grows cubically. It's incredibly inefficient because if you think about it, most of that 3D space is just empty air, which means your computer is working overtime just to memorize a whole bunch of nothing. Because voxels are so incredibly heavy on memory, the industry heavily relies on that first encoding type we mentioned, the point cloud. A point cloud is exactly what it sounds like. It's a massive, totally unordered, and highly sparse set of X, Y, and Z coordinates. It only samples the physical surfaces that the sensor actually hits, and it just leaves the empty space completely alone. It really is the rawest, most direct translation of the physical world straight into digital data. Let's actually ground this concept in reality for a minute. Just take a look at this. This is how an autonomous vehicle practically visualizes its environment out on the road. It uses active sensing, like LiDAR, shooting out laser pulses to instantly measure the exact physical geometry of everything around it in real time. The resulting 3D point cloud is quite literally what the car sees. But, as you might guess, just having a bunch of dots isn't enough. The computer actually has to understand what those dots mean. Which leads perfectly into Section 3, making sense of point clouds, teaching AI the z-axis. Feeding a wild point cloud into a neural network used to be a monumental challenge. Why? Well, unlike the neat little pixels in a photo, point clouds have absolutely no order and no grid. They are just a chaotic list of random coordinates.
But then enter PointNet. This was a massive breakthrough for the field. PointNet was the very first deep network architecture that could directly process these unordered point clouds. And it did this through a concept called permutation invariance, by using a really clever mathematical trick, specifically symmetric max pooling. Think of it kind of like a bag of mixed Legos. The network doesn't actually care what order you pull them out of the bag. It just inherently understands the overall collection of shapes. Now, vanilla PointNet was great, but it kind of looked at the whole shape all at once, so it missed the fine local details. To fix that, researchers created PointNet++. They introduced this brilliant three-step process called the set abstraction layer. First, it uses farthest point sampling to pick a few widely spaced seed points. Second, it uses a ball query to group all the raw points within a certain radius of those seeds. And third, it just runs a mini local PointNet on those small clusters. By doing this hierarchically, the AI learns local geometric structures perfectly, kind of like how a 2D network learns the edges of something before it learns the whole face. Okay, so now that the AI understands geometry, we needed to actively detect real-world objects so things like cars don't crash. Moving to Section 4, Fusing Sensors for Detection, the multimodal mind. So if you're building a self-driving car right now, what sensor do you actually use? Well, this matrix pretty much tells the whole story. LiDAR gives you incredibly high spatial accuracy, but it's really expensive, and lasers notoriously struggle in heavy rain or fog. Cameras, on the other hand, are super cheap and they give you rich semantic details, like color and text, but they totally lack that native depth precision we talked about earlier. So the absolute best, most robust approach, you combine them. We absolutely need the precise geometry of LiDAR paired with the rich texture of cameras. But how do you actually fuse flat 2D camera pixels with sparse 3D LiDAR points? I mean, they don't even speak the same language. Well, this is where BV Fusion comes in, and it's a real game changer. BV Fusion is a state-of-the-art framework that takes the dense features from multiple cameras, lifts them up into 3D, and then projects both that camera data and the LiDAR geometry down into a single, unified bird's-eye view, or BEV space. By looking at the world from this top-down, multimodal perspective, the AI achieves a dramatically higher accuracy in object detection. This fusion is absolutely crucial for robust, life-saving autonomous perception out in the real world. Section 5. Rendering New Realities, from Detection to Generation. Okay, so far, we've mostly just been asking, where are the objects? But now, we've reached the climax of our explainer. We are going to change the question entirely. Instead of just detecting objects, we're going to ask, what does the full scene actually look like? Get ready, because I found this part absolutely mind-blowing. Enter neural radiance fields, or as they're commonly known, NeRFs. Instead of building a clunky 3D mesh, a NeRF uses a neural network, a multi-layer perceptron specifically, to literally memorize an entire continuous 3D scene. You train it by just showing it a bunch of 2D images from different angles. Then, you query the network with a 5D input, an X, Y, Z position in space, plus whichever direction you're looking. And the network magically outputs the exact density and RGB color for that specific point in space. The result? You can render stunningly realistic, brand new viewpoints of a scene that a camera never even captured. Now, MRFs are beautiful, for sure, but they are computationally really slow, mostly because the network has to calculate thousands of points along every single ray of light. But recently, a brand new technique called 3D Gaussian splatting hit the scene and just blew the doors off the industry. By representing the scene as millions of tiny 3D Gaussian blobs that can be rapidly projected and blended right onto a screen, we achieve rendering speeds up to 100 times faster than a standard NeRF. We're talking about photorealistic, real-time novel view synthesis happening entirely on the fly. It is wild. And that brings us to Section 6, the AI generation leap, the final frontier. This right here is the absolute cutting edge, the final frontier, where AI stops merely interpreting reality and literally starts creating it from scratch. Just like we have massive foundation models for text, like ChatGPT, we now have foundation models for 3D. Models like Uni3D use billion-scale learning to align point clouds perfectly with text and image embeddings in a shared feature space. And then models from OpenAI, like PointE and ShapeE, take this a whole step further using diffusion. They allow you to type a simple text prompt, and the AI will literally generate a fully realized 3D point cloud or mesh right out of thin air. We are completely bridging the gap between human language and 3D geometry. Which leaves us with this final, kind of provocative thought to chew on. We started all this by just trying to help computers simply see the depth in front of them so cars wouldn't crash into things. But now, we are standing right at the edge of a totally new era.
If an AI can understand spatial geometry so perfectly that it can generate a photorealistic 3D world from just a single text prompt, what actually happens to reality? When the virtual becomes completely indistinguishable from the physical, how will we navigate the worlds we build next? Thank you so much for joining me on this explainer. I really hope this sparked your curiosity about the incredible future of 3D vision. See you next time.